Hello and welcome to Fundamentals of Cybersecurity, CSCI150N Chapter 18, Secure Software Development. I'm your instructor, Peter Keurig, and welcome. In this chapter, you will learn how to describe how secure coding can be incorporated into software development process, list the major types of coding errors and their root causes, describe good software development practices, and explain how they impact application security. Describe how using a software development process enforces security inclusion in a project, and learn about application hardening techniques. The lecture outline for this chapter includes the software engineering process, secure coding concepts, application attacks, and application hardening. For the software engineering process, the book provides several process models. Process models are waterfall model, spiral model, agile model, evolutionary model, and secure development lifecycle model. The book does a good job in explaining each one of these. I highly recommend you go through and have at least a general familiarization with the types of processes that are out there in case you are hired into an organization where you'll be working with the software developers. Secure development lifecycle. The common security coding requirements include analysis of security and privacy risks, authentication and password management, audit logging and analysis, authorization and role management, code integrity and validation testing, cryptography and key management, data validation and sanitization, network and data security, ongoing education and awareness, team staffing requirements, and third-party component analysis. With error and exception handling, every application will encounter errors and exceptions, and these need to be handled in a secure manner. One attack methodology includes forcing errors to move an application from normal operation to exception handling. During an exception, it is common practice to report the condition, including supporting information such as data that resulted in the error. This information can be invaluable in diagnosing the cause of the error condition. The challenge is in where this information is captured. The best method is to capture it in a log file, where it can be secured by an ACL. The worst case is when it's echoed to the user, and echoing error conditions details to users can provide valuable information to attackers when they cause errors on purpose. Improper exception handling can lead to a wide range of disclosures. Errors associated with SQL statements can disclose data structures and data elements. Remote procedure call errors can give up sensitive information such as file names, paths, and server names. Problematic errors can give up line numbers that an execution occurred on, the method that was involved, and the information such as stack elements. With input and output validation, with the move to web-based applications, the errors have shifted from buffer overflows to input handling issues. Users have the ability to manipulate input, so it is up to the developer to handle the input appropriately to prevent malicious entries from having an effect. Buffer overflows could be considered a class of improper input, but newer attacks include cannibalization attacks and arithmetic attacks. Probably the most important defensive mechanism that can be employed is input validation. Considering all inputs to be hostile until properly validated can mitigate many attacks based on common vulnerabilities. This is a challenge as the validation efforts need to occur after all parsers have completed manipulating input streams, a common function in web-based applications using Unicode and other international character sets. So if you've ever been on a web page and you want to enter in your information, such as your phone number or your social security number, and it wasn't properly formatted and it gave you an error message, that's part of the validation process for that web page. Now, one of the most powerful tools that can be used in testing is fuzzing, aka fuzz testing, which is the systematic application of a series of malformed inputs to test how the program responds. Fuzzing has been used by hackers for years to find potentially exploitable buffer overflows without any specific knowledge of the coding. Fuzz testing works perfectly fine regardless of the type of testing, white box or black box. Fuzzing serves as a basic practice for finding unexpected input validation errors. A tester can use a fuzzing framework to automate numerous input sequences. In examining whether a function could fall prey to a buffer overflow, a tester can run enormous inputs, testing lengths and ultimately payload delivery options. If a particular input string results in a crash that can be exploited, the tester would then examine this input in detail. Fuzzing is still relatively new to the development scene, but is rapidly maturing and will soon be nearly equal footing with other automated code checking tools. Bug tracking is a foundational element in secure development. All bugs are enumerated, classified, and tracked. If the classification of a bug exceeds a set level, then it must be resolved before the code advances to the next level of development. Bugs are classified based on the risk the vulnerability exposes. Microsoft uses 4 levels: critical, important, moderate, and low. Examples of critical vulnerabilities include those that without warning to the user can result in remote exploits involving elevation of privilege. Attacks against a system can occur at the network level, at the operating system level, at the application level, or at the user level. Early attack patterns were against the network, but most of today's attacks are aimed at the applications, primarily because that is where the objective of most attacks resides. In the infamous words of the bank robber Willie Stone, because that is where the money is. Application-level attacks take advantage of several facts associated with computer applications. First, most applications are large programs written by groups of programmers and by their nature have errors in design and coding that create vulnerabilities. For a list of typical vulnerabilities, see the Common Vulnerabilities and Exposure list maintained by MITRE. Second, even when vulnerabilities are discovered and patched by software vendors, end users are slow to apply patches, as evidenced by the SQL Slammer incident in January 2003. The vulnerability exploited was a buffer overflow, and the vendor supplied a patch 6 months prior to the outbreak, yet the worm still spread quickly due to the multitude of unpatched systems. Cross-site scripting is one of the most common web attack methodologies. A cross-site scripting attack is a code injection attack in which an attacker sends code in response to an input request. This code is then rendered by the web server, resulting in the execution of the code by the web server. Cross-site scripting attacks take advantage of a few common elements in web-based systems. First is the common failure to perform complete input validation. Cross-site scripting sends scripts in response to an input request, even when script is not the expected or authorized input type. Second is the nature of the web-based systems to dynamically self-create output. Web-based systems are frequently collections of images, text, scripts, and more, which are presented by a web server to a browser that interprets and renders. Cross-site scripting attacks can exploit the dynamically self-created output by executing a script in the client browser that receives the altered output. The cause of the vulnerability is weak user input validation. If input is not validated properly, an attacker can include a script in their input and have it render as part of the web process. There are several different types of cross-site scripting attacks, which are distinguished by the effects of the script. Non-persistent cross-site attacks: the injected script is not persisted or stored, but rather is immediately executed and passed back via the web server. Persistent cross-site scripting attacks: the script is permanently stored on the web server or some back-end storage. This allows the script to be used against others who log into the system. DOM-based cross-site scripting attacks: the script is executed in the browser via the Document Object Model DOM process as opposed to the web server. Cross-site scripting attacks can result in a wide range of consequences, and in some cases, the list can be anything that a clever scripter can devise. Common uses that have been seen in the wild include the following: theft of authentication information from a web application, session hijacking, deploying hostile content, changing user settings including future users, impersonating a user, phishing, or stealing sensitive information. The use of input to a function without validation has already been shown to be risky behavior. Another issue with unvalidated input is the case of code injection. Rather than input being appropriate for the function, this code injection changes the function in an unintended way. A SQL injection attack is a form of code injection aimed at any structured query language-based database, regardless of vendor. LDAP-based systems are also subject to injection attacks. When an application constructs an LDAP request based on user input, a failure to validate the input can lead to bad LDAP requests. Just as the SQL injection can be used to execute arbitrary code in a database, the LDAP injection can do the same in a directory structure. Something as simple as a wildcard character in a search box can return results that would normally be beyond the scope of a query. Proper input validation is important before passing the request to an LDAP engine. XML injections can be used to manipulate an XML-based system. As XML is nearly ubiquitous in the web application world, this form of attack has a wide range of targets. The primary method of defense against injection attacks is similar to that of a buffer overflow. Validate all inputs. But rather than validating towards just length, you need to validate inputs for content. Imagine a web page that asks for a user input and then uses that input in the building of a subsequent page. Also imagine that the user puts the text for a JavaScript function in the middle of their input sequence, along with a call to the script. Now, the generated web page has an added JavaScript function that is called when displayed. Passing the user input through the HTML encode function before use can prevent such attack. A directory traversal attack is when an attacker uses special input to circumvent the directory tree structure of the file system. Adding encoded symbols for ... in an unvalidated input box can result in the parser resolving the encoding to the traversal code, bypassing many detection elements and passing the input to the file system, resulting in the program executing commands in a different location than designed. When combined with a command injection, the code can result in execution of code in an unauthorized manner. Classified as input validation error, these can be difficult to detect without doing code walkthroughs and specifically looking for them. This illustrates the usefulness of the top 25 most dangerous software errors checklist during code review, as it would alert developers to this issue during development. Directory traversal can be masked by using encoding of input streams. If the security check is done before the string is decoded by the system parser, then recognition of the attack form may be impaired. There are many ways to represent a particular input form, the simplest of which is the canonical form. Parsers are used to render the canonical form for the OS, but these embedded parsers may act after input validation, making it more difficult to detect certain attacks from just matching a string. If there is one item that can be labeled as the most wanted in coding security, it would be the buffer overflow. If you have noticed, we have talked about it several times in the last few chapters. Nearly half of all exploits of computer programs stem historically from some form of buffer overflow. Finding a vaccine to buffer overflow would stamp out about half these security-related incidents by type and probably 90% by volume. The concept behind these vulnerabilities is relatively simple. The input buffer that is used to hold program input is overwritten with data that is larger than the buffer can hold. The root cause of this vulnerability is a mixture of two things: poor programming practices and programming language weaknesses. An integer overflow is a programming error condition that occurs when a program attempts to store a numeric value, or an integer, in a variable that is too small to hold it. The results vary by language and numeric type. In some cases, the value saturates the variable, assuming the maximum value for the defined type and no more. Integer overflows are easily tested for, and static code analyzers can point out where they are likely to occur. Given this, there are not any good excuses for having these errors end up in production code. Cross-site request forgery attacks utilize unintended behaviors that are proper in defined use but are performed under circumstances outside the authorized use. A cross-site reference forgery attack relies upon several conditions to be effective. It is performed against sites that have an authenticated user and exploits the site's trust in a previous authentication event. Then by tricking a user's browser to send an HTML request to the target site, the trust is exploited. So assume your bank allows you to log in and perform financial transactions, but does not validate the authentication of each subsequent transaction. If a user is logged in and has not closed their browser, then an action in another browser tab can send a hidden request to the bank, resulting in a transaction that appears to be authorized, but in fact was not done by the user. There are many different mitigation techniques that can be employed, from limiting authentication times to cookie expirations to managing some specific element of a web page like header checking. The strongest method is the use of random cross-site request forgery tokens in form submissions. Subsequent requests cannot work as the token was not set in advance. Testing for cross-site request forgery takes a bit more planning than for other injection type attacks, but this too can be accomplished as part of the design process. 0 day is a term used to define vulnerabilities that are newly discovered and not yet addressed by a patch. Most vulnerabilities exist in an unknown state until discovered by a researcher or the developer. If a researcher or a developer discovers a vulnerability but does not share the information, then this vulnerability can be exploited without a vendor's ability to fix it. Because for all practical knowledge the issue is unknown, then the vulnerability can be exploited without a vendor's ability to fix it, because for all practical knowledge the issue is unknown, except for the person who found it. From the time of the discovery until a fix or a patch is made available, the vulnerability goes by the name 0 day, indicating that it has not been addressed yet. Some other application attacks include attachments. Attachments can also be used as an attack vector. If a user inputs a graphic file, for instance a JPEG file, and that file is altered to contain executable code such as Java, then when the image is rendered, the code is executed. This can enable a wide range of attacks. Locally shared objects are pieces of data that are stored on a user's machine to save information from an application, such as a game. Frequently these are cookies used by Adobe Flash called Flash cookies and can store information such as user preferences. As these can be manipulated outside of the application, they can represent a security or privacy threat. Client-side attacks. The web browser has become the major application for users to engage resources across the web. One of the risks involved in taking user input and using it to create a command to be executed on a system is arbitrary or remote code execution. This attack involves an attacker preparing an input statement that changes the form or function of a prepared statement. A form of command injection, this attack can allow a user to insert arbitrary code and then remotely execute it on a system. This is a form of input validation failure, as users should not have the ability to change the way a program interacts with the host OS outside of a set of defined and approved methods. Open Vulnerability and Assessment Language, or OVAL. The MITRE Corporation has developed a taxonomy of vulnerabilities, Common Vulnerability and Exposure, or CVE, in an effort to make machine-readable data exchanges to facilitate system management across large enterprises. The CVE led to efforts such as the development of the Open Vulnerability and Assessment Language, OVAL. OVAL comprises two main elements: an XML-based machine-readable language for describing vulnerabilities, and a repository. Additional efforts by MITRE include the following: Common Attack Pattern Enumeration Classification, Extensible Configuration Checklist Description Format, Security Content Automation Protocol, Common Configuration Enumeration, Common Platform Enumeration, Common Weak Enumeration, and Common Event Expression, and Common Result Format. Application hardening works in the same fashion as system hardening. The first step is the removal of unnecessary components or options. The second step is the proper configuration of the system as it is implemented. It can lead to changes to these conditions, and they should be confirmed after each update. The primary tools used to ensure a hardened system are a secure application configuration baseline and a patch management process. A baseline is a set of proper settings for a computer system. An application configuration baseline outlines the proper settings and configuration of an application or set of applications. These settings include many elements, from application settings to security settings. Protection of the settings is crucial, and the most common mechanisms used to protect them include access control lists and protected directories. The documentation of desired settings is an important security document assisting administrators in ensuring that proper configuration are maintained across updates. Application patch management is a fundamental component of application and system hardening. The objective is to run the most secure version of an application, and, with few exceptions, that would be the most current version of software, including patches. Most updates and patches include fixing security issues and closing vulnerabilities. Current patching is a requirement of many compliance schemes as well. Patching does not always go as planned, and some patches may result in problems in production systems. A formal system of patch management is needed to test and implement patches in a change-controlled manner. Current programming trends includes topics such as whether to use SQL databases or non-SQL databases. SQL databases are those that use structured query language to manipulate items that are referenced in a relational manner in the form of tables. NoSQL refers to data stores that employs neither SQL nor relational table structures. Each system has its strengths and weaknesses, and both can be used for a wide range of data storage needs. In modern client-server environments, data can be checked for compliance with input/output requirements either on the server or on the client. There are advantages to verifying data elements on a client before sending to the server. Name, efficiency, doing checks to the server, namely efficiency. Doing checks on the client saves a round trip and delays before a user can be alerted to a problem. This can improve the usability of software interfaces. I'm your instructor, Peter Keurig, for Nashville Community College. Thank you for watching.